What if I told you that right now, as you sit watching this, the universe is screaming at us in the most violent, energetic language it knows, not with sound, not with visible light, but with gamma rays, the highest energy photons racing across space, carrying secrets we've only begun to unravel. Picture this: every second, your body is gently peppered by these invisible messengers from the cosmos, remnants of cataclysmic explosions, black hole eruptions, and phenomena so bizarre they defy our current understanding of physics. Yet, despite decades of study, the gamma-ray background, this faint, omnipotent glow saturating the universe, remains one of astronomy's greatest unsolved puzzles. We're talking about light so powerful, a single gamma-ray photon carries millions of times the energy of visible light, capable of tearing atoms apart. But here's the twist: when we point our telescopes at the sky, we don't just see gamma rays from known sources like pulsars or supernova. Instead, we find a mysterious, uniform haze stretching across the cosmos, a fog of high-energy radiation with no clear origin. It's as if the universe left its porch light on and no one can figure out who or what flipped the switch. Some scientists suspect hidden galaxies teeming with unimaginable violence. Others whisper about exotic particles decaying in deep space, or even relics from the birth of the universe itself. The truth, we simply don't know. That's where the adventure begins. Over the next 25 mysteries, we'll journey through the most electrifying enigmas of the gamma-ray background, from the unsettling voids where gamma rays vanish without a trace, to bizarre blobs of energy that seem to pulse in sync across billions of light years. We'll confront theories that blur the line between science and science fiction, and meet the brilliant minds racing to decode what Einstein once called the universe's most furious whispers. So buckle up. By the end, you'll never look at the night sky or the invisible energy seething through it the same way again. The cosmos is shouting. It's time we listen. The first mystery we encounter is as unsettling as it is beautiful: a uniform sea of gamma rays stretching across the entire sky like an invisible aurora. If these gamma rays came from ordinary cosmic powerhouses, active galaxies, colliding neutron stars, or supernovae, we'd expect them to clump together, tracing the outlines of their violent births. Instead, the glow is eerily smooth, as if someone took a high-energy paintbrush and coated the universe in a single, seamless stroke. So what could possibly create such an even, all-encompassing signal? One leading suspect is dark matter, the elusive substance that makes up 85% of the universe's mass. Some theories suggest dark matter particles might annihilate when they collide, releasing gamma rays as their final scream into the void. If true, this glow could be the shadow of an invisible cosmic war raging all around us. But there's a catch: our most sophisticated simulations predict dark matter should clump in halos around galaxies, not spread evenly. The gamma-ray background doesn't match the map we'd expect. Then there's the wild card: primordial black holes. These hypothetical relics, forged in the first chaotic seconds after the Big Bang, could be peppered throughout space, evaporating slowly and unleashing gamma rays as they fade. Yet even here, the math doesn't quite add up. If these black holes were common enough to explain the glow, we'd see their fingerprints elsewhere, distorting starlight, warping galaxies, and so far those clues remain missing. The Fermi Gamma Ray Space Telescope threw gasoline on the mystery. By mapping the sky with unprecedented precision, it revealed something even stranger. The glow isn't just uniform, it's too bright. Known gamma-ray sources account for less than half the radiation we see. The rest, a cosmic blank check waiting for someone or something to fill in the name. Perhaps the answer lies in the unseen, in galaxies so faint they're lost in the glare of their own brilliance. Or maybe it's something far stranger, a process we haven't even imagined yet. The diffuse gamma glow isn't just a puzzle, it's a mirror, reflecting how much we still don't understand about the universe's hidden mechanics, and that's what makes this mystery so thrilling. Every unanswered question is an invitation to look deeper. Blazars, the universe's natural particle accelerators, should be drowning the cosmos in gamma rays. These monstrous active galaxies, powered by supermassive black holes, fired jets of radiation directly at Earth like a cosmic lighthouse beam aimed straight at our telescopes. For years, astronomers assumed blazars were the primary culprits behind the gamma-ray background, their combined fury painting the sky in high-energy light. But when researchers tallied up their total output, the numbers didn't just fall short, they revealed a glaring gap in our understanding. Even with thousands of blazars counted, their contribution accounts for less than half of the gamma rays we observe. This discrepancy, dubbed the blazar paradox, has sent scientists scrambling for answers. If blazars aren't the dominant source, what's flooding the universe with the rest of this radiation? One possibility is that we're missing an entire population of hidden blazars galaxies whose jets aren't pointed directly at us, making them invisible to our detectors. But even after accounting for these shy cosmic giants, the math still leaves a staggering void. Then there's the wilder possibility: rogue particle accelerators lurking in the emptiness between galaxies. Picture vast magnetic fields stretching across intergalactic space, whipping stray electrons to near light speeds until they smash into photons, transforming them into gamma rays. These invisible cosmic webs could be secretly energizing the universe's background glow. Even more intriguing are the whispers of something beyond known physics. Some theorists suggest decaying dark matter could be injecting gamma rays into the void, while others propose primordial turbulence from the Big Bang left behind pockets of seething energy. But the most unsettling idea, that we're seeing the fingerprints of entirely new celestial phenomena, objects or processes so exotic we haven't even conceived of them yet. The irony is delicious. Blazars, once thought to be the undisputed kings of the gamma-ray sky, now serve as a reminder of how much is still hidden from us. Every time we think we've mapped the universe's most violent engines, the cosmos humbles us with another riddle. And that's the beauty of this mystery. It's not just about missing light. It's a spotlight on the frontiers of our ignorance, illuminating the gaps where discovery waits. Now let's zoom in from the vast cosmic backdrop to our own galactic neighborhood, specifically the heart of the Milky Way. Here, astronomers have stumbled upon a bizarre anomaly, a mysterious excess of gamma rays blooming from the region around our galaxy's supermassive black hole. It's not the smooth haze we see across the universe, but a concentrated hump of energy that defies easy explanation. This so-called Galactic Center excess has become one of the most hotly debated puzzles in modern astrophysics, with two leading theories locked in a tug-of-war. On one side, there's the tantalizing possibility that we're witnessing dark matter's grand finale. According to this idea, invisible particles of dark matter, likely WIMP, or weakly interacting massive particles, could be annihilating each other in the dense gravitational field at the galaxy's core. As they collide and obliterate, they'd unleash a cascade of gamma rays, creating the exact kind of excess we observe. It's an elegant solution, one that would finally give us tangible evidence of dark matter's nature after decades of searching. But there's a problem. The signal isn't quite as crisp as models predict. Instead of a sharp spike, the gamma-ray hump is oddly puffy, like a smudged fingerprint. That fuzziness leads us to the other contender, a swarm of pulsars. These ultra-dense, spinning stellar corpses emit gamma-ray beams like cosmic lighthouses, and the Milky Way's center is packed with them. The catch: many could be too faint or crowded together for our telescopes to resolve individually, blending into what looks like a single, glowing excess. Enter artificial intelligence. In recent years, machine learning algorithms have scoured the data, swinging the argument like a pendulum. One study might claim the excess is too smooth to be pulsars, favoring dark matter. Another counters that AI-detected point sources match pulsar behavior perfectly. The debate grows even thornier when you consider that both explanations could be true. Pulsars and dark matter might be contributing to the signal, their gamma rays entangled like voices in a crowded room. What makes this mystery so electrifying is the stakes. If it's dark matter, we're on the verge of a historic breakthrough. If it's pulsars, we're uncovering hidden chapters of our galaxy's violent history. Either way, the Galactic Center excess isn't just a scientific dispute. It's a masterclass in how the universe keeps us guessing. Every time we think we're close to an answer, the data throws us a curveball, reminding us that even in our own cosmic backyard, the unknown lurks just beneath the surface. Rising from the Milky Way's core like twin cosmic geysers, the Fermi Bubbles stretch 50,000 light-years into the void, one above our galaxy, one below, glowing with gamma rays so intense they outshine the rest of the galactic plane. Discovered just over a decade ago, these colossal structures shouldn't exist based on our understanding of galactic physics. Their sheer scale defies logic. If they were visible to the naked eye, they'd span half the night sky. But here's the real puzzle. The energy signature of these bubbles doesn't match the aftermath of a supermassive black hole eruption, the most obvious suspect. When black holes belch, they typically leave behind chaotic, uneven debris fields. The Fermi bubbles, by contrast, are eerily symmetrical and filled with strangely uniform gamma-ray fog, as if sculpted by an unseen hand. So what cosmic sculptor could carve such perfection? One theory points to an ancient cataclysm. Roughly 6 million years ago, our galaxy's central black hole, Sagittarius, a star, might have gorged on a massive gas cloud, triggering a quasar-like explosion. The resulting shockwaves could have inflated these bubbles like cosmic balloons, but simulations show a problem. Such an outburst would have also shredded nearby star clusters and left scars in the galactic disk, scars we don't see. Enter the dark matter storm hypothesis. Imagine invisible particles colliding in the galaxy's gravitational well, their annihilation sparking gamma-ray tsunamis that blew these bubbles outward. It's a compelling idea, except for one hiccup: the bubble's edges are razor-sharp, unlike the fuzzy boundaries dark matter interactions usually produce. Then there's the antimatter wildcard. If pockets of primordial antimatter survived from the Big Bang, drifting into the galactic center, their annihilation with normal matter could have unleashed the energy needed. But antimatter doesn't just linger for billions of years, it seeks out and destroys regular matter on contact. For this to work, we'd need a mysterious mechanism constantly replenishing it, like a hidden antimatter fountain near Sagittarius, a star. The most tantalizing clue lies in the bubble's gamma-ray skin. Unlike their smooth interiors, the edges crackle with high-energy electrons, suggesting an ongoing acceleration process. Some researchers propose these are cosmic particle accelerators, powered by the galaxy's magnetic field twisting into colossal vortexes. Others wonder if we're seeing echoes of a long-lost galaxy merger, where a smaller black hole spiraled into Sagittarius, a star, kicking up these structures like pebbles in a pond. The Fermi bubbles force us to confront an uncomfortable truth. Our galaxy might have a violent, unpredictable heartbeat we barely understand. Every explanation we propose feels like grasping at cosmic straws, revealing gaps in our knowledge as vast as the bubbles themselves. And that's what makes these ghostly structures so magnetic. They're not just a mystery. They're a mirror, reflecting how even the familiar Milky Way still guards secrets that rewrite the rules of astrophysics. Lightning cracks across the sky, a familiar spectacle, yet hidden within those brilliant forks lies one of nature's most explosive secrets. During thunderstorms, Earth itself fires gamma-ray bursts into space, violent flashes so powerful they rival emissions from distant neutron stars. These terrestrial gamma-ray flashes, or TGF, last mere milliseconds, but their energy defies belief. A single bolt can hurl electrons to near light speed, slamming them into the atmosphere until they unleash gamma rays potent enough to be detected by satellites. For decades, we assumed gamma rays were born in the cosmos, not our own backyard. Then, in the 1990s, orbiting sensors picked up these brief, intense bursts emanating from storm clouds. The discovery flipped atmospheric physics on its head. Lightning, it turns out, isn't just electricity, it's a natural particle accelerator. Here's how it works. In the heart of a thunderstorm, electric fields grow so strong they rip electrons from air molecules, flinging them upward like cosmic pinballs. As these electrons collide with atoms, they emit gamma rays, which in turn spawn more high-energy particles in a runaway avalanche. But the real shock came when researchers realized some TGFs weren't just raining down, they were shooting upward, escaping Earth entirely. These inverted bursts suggest thunderstorms might be acting like giant gamma-ray guns firing into space. The leading theory: cosmic rays' high-energy particles from distant supernova trigger the process. When a cosmic ray slams into the upper atmosphere, it could seed a cascade of electrons, supercharging the storm's electric fields and launching gamma rays skyward. The implications are staggering. If thunderstorms can accelerate particles to such extreme energies, they might be contributing to the radiation belts surrounding Earth, even influencing the chemistry of the upper atmosphere. Some scientists speculate TGFs could pose risks to aircraft, their gamma rays intense enough to penetrate plane hulls. Others wonder if similar processes occur on other planets. Imagine Jupiter's raging storms unleashing gamma-ray tempests. Yet mysteries linger. Why do only some lightning bolts produce TGFs? How do these bursts escape the atmosphere without being absorbed? And could they be linked to rare, enigmatic phenomena like sprites, those ghostly electrical discharges that dance above thunderstorms? Every TGF we detect is a reminder that even Earth's most familiar forces still guard secrets, blurring the line between our world and the cosmos. The universe's highest energy light isn't just out there, it's crackling right above us, a whisper of the cosmic violence hiding in the storm clouds. In August 2017, the universe handed astronomers a treasure chest and then promptly broke the lock. That month, detectors picked up something unprecedented: gravitational waves rippling from a cataclysm 130 million light-years away, followed seconds later by a burst of gamma rays. The source, two neutron stars, each more massive than our Sun but no wider than a city, spiraling into each other in a final, violent embrace. This cosmic collision, dubbed GRB 170817A, should have been an open and shut case. Neutron star mergers were predicted to create short gamma-ray bursts, and here was textbook proof. But then the universe threw a curveball. Instead of fading within days as expected, the afterglow kept brightening, first in X-rays, then in gamma rays. By 2018, it was glowing brighter than it had at peak, defying every model. Imagine throwing a rock into a pond and watching the splash grow taller instead of shrinking. That's the level of absurdity scientists faced. Normally, neutron star collisions fire jets of material at nearly light speed, and when these jets plow into surrounding gas, they create a brief, predictable afterglow. But GRB 170817A's jet didn't behave. It seemed to be feeding on some hidden energy source, like a cosmic engine that refused to shut off. One radical theory suggests the collision birthed a magnetar, a neutron star on steroids with a magnetic field a quadrillion times stronger than Earth. As this newborn monster spins, its magnetic brakes could be converting rotational energy into radiation, pumping the afterglow like a cosmic bellows. But there's a hitch: magnetars usually fade within weeks, this one's still sputtering years later. Then there's the dark horse explanation, a cocoon of debris. If the merger's jet got bogged down in its own wreckage, it might have heated the surrounding material into a lingering, radiant haze. Yet simulations show even this shouldn't last as long as what we're seeing. The most tantalizing possibility: we're witnessing an entirely new astrophysical phenomenon, one where neutron star mergers don't just fade quietly but leave behind engines of destruction that churn for years. GRB 170817 isn't just rewriting the rules, it's scribbling in the margins, daring us to rethink how the universe's most extreme events play out. Every extra day this afterglow persists, it whispers a challenge. You thought you understood me? Think again. Stare at any patch of the night sky long enough, and you'll see stars, galaxies, cosmic landmarks we've catalogued for centuries. But gamma rays don't play by those rules. Point a gamma-ray telescope upward, and you'll find something unnerving. Roughly 75% of these high-energy photons arrive from nowhere. No galaxies, no black holes, no remnants of stellar explosions, just voids where our best instruments see nothing at all. Scientists call this the empty sky paradox, and it's one of the most humbling holes in modern astronomy. If gamma rays are cosmic screams, why are we hearing them from rooms we're sure are empty? One radical idea twists the fabric of reality itself: cosmic strings. These hypothetical cracks in space-time, thinner than an atom but stretching across the universe, could be vibrating like snapped guitar strings from the Big Bang's aftermath. As they wiggle, they might release bursts of gamma-rays particles born not from stars or collisions, but from space-time itself unraveling. The catch: cosmic strings are so elusive they'd leave no other trace. We'd only detect their faint gamma-ray hum, like hearing a distant bell toll in a fog. Then there's the quantum foam theory. At the smallest scales, space-time isn't smooth. It's a seething, frothing mess where particles pop in and out of existence. Occasionally, these quantum fluctuations could release energy in gamma-ray bursts, sprinkling the sky with phantom light. It's as if the vacuum of space itself has a heartbeat, faint but detectable. But the wildest possibility might be the simplest: we're missing something obvious. Consider that gamma rays can travel billions of years before reaching us. By the time they arrive, their sources, like dim galaxies or dying black holes, could have faded into oblivion, leaving only their high-energy echoes. Or perhaps entire classes of cosmic objects emit gamma rays in ways we don't yet recognize, like invisible lighthouses flashing in frequencies we're only beginning to see. The empty sky paradox forces us to confront how much of the universe operates in the shadows. Every unexplained gamma ray is a breadcrumb leading to a frontier we've barely mapped, a reminder that the cosmos isn't just stranger than we imagine, but stranger than we can imagine. And that's the thrill of the hunt. The answers we seek might not lie in the stars, but in the voids between them. Our galaxy wears a ghostly cloak, one that glows with gamma rays where no light should be. Stretching tens of thousands of light years beyond the Milky Way's familiar spiral arms, an enigmatic haze envelops everything like a cosmic fog. This isn't starlight. It's not the usual radiation from gas clouds or dying stars. It's something far stranger, an anomalous gamma-ray halo pulsing with energy we can't yet explain. The first clue came when astronomers subtracted all known sources of gamma-rays pulsars, supernova remnants, colliding particles from the Milky Way's emissions. What remained was this vast, diffuse glow clinging to our galaxy like an aura. At first glance, it seemed like a smoking gun for dark matter. After all, if invisible particles are colliding and annihilating throughout the galaxy's gravitational grasp, wouldn't their gamma-ray whispers form exactly this kind of halo? The math almost fits, but here's the twist: the halo's energy signature doesn't match predictions. Dark matter annihilation should produce a smooth, symmetrical glow, peaking at specific energy levels. Instead, this halo is patchy, its gamma rays skewed toward higher energies, as if something's accelerating particles violently within the void. That's led some scientists to an even wilder idea: a hidden population of cosmic rays rocketing through space at speeds we've never measured. Imagine rogue protons stripped of electrons and hurled outward by magnetic fields so vast they span the galaxy. these hyper-fast particles could slam into slower-moving matter, sparking gamma-ray cascades. But what could possibly launch them? One theory points to the Milky Way's own supermassive black hole, which might have erupted in a forgotten outburst, flooding the halo with accelerated debris. Another suggests collapsing stars in the galaxy's outskirts are acting as natural particle cannons. Then there's the curveball, the halo's uneven texture. Recent maps reveal it's brighter on one side of the galaxy than the other, as if something, a passing dwarf galaxy, perhaps has stirred the pot. If true, it would mean the halo isn't static. It's dynamic, shifting over millennia like weather in an unseen atmosphere. The deeper we look, the more this gamma-ray fog refuses to fit neatly into any box. It taunts us with possibilities, a dark matter graveyard, a cosmic ray accelerator, or even a combination of both. Every new observation peels back another layer, revealing just how much we still don't understand about the invisible forces sculpting our galactic home. The Milky Way's halo isn't just a mystery, it's a mirror, reflecting how much of the universe's story remains written in light we're only beginning to decode. Time itself might be unraveling in the heart of some gamma-ray bursts. Imagine watching a firework explode, but instead of seeing the blast expand outward, you catch glimpses of the explosion rewinding, fragments of light crawling backward in time. That's the baffling phenomenon astronomers have dubbed time-reversed gamma signals, where certain high-energy bursts arrive with their components inverted, as if the universe hit rewind on a cosmic tape player. The first hints emerged in data from the Fermi Gamma-Ray Space Telescope. Normally, gamma-ray bursts follow a predictable pattern, a sharp spike as the explosion reaches its peak, followed by a gradual fade. But a handful of these events flout the rules. Their light curves, the graph of how brightness changes over time, contain eerie echoes that mirror the main burst backwards, like a reflection in a temporal funhouse mirror. It's not just an oddity, it's a violation of causality, the bedrock principle that cause must precede effect. Scientists scrambled for mundane explanations. Could it be an instrumental artifact, some glitch in the detectors? After painstaking analysis, the answer was a resounding no. The signals were real, their inverted structure etched into the data with chilling precision. That left only one unsettling possibility. We might be staring at the fingerprints of physics beyond Einstein's relativity. Enter tachyons, the hypothetical particles that haunt the edges of theoretical physics. These phantoms of the quantum world are thought to travel faster than light, a property that would bizarrely make them experience time in reverse. If tachyonic particles exist, their decay could produce gamma rays with this telltale inverted signature, like cosmic breadcrumbs leading back to a realm where time flows backward. The implications are dizzying. Not only would this rewrite our understanding of causality, but it could open doors to phenomena like precognition in quantum systems or even time loops woven into the fabric of space itself. Yet not everyone's ready to embrace time-bending particles. Some theorists argue the answer lies in the chaotic environments around black holes, where gravitational lensing, light bending around extreme space-time warps, could create the illusion of reversed signals. Picture a gamma ray burst near a spinning black hole. Its light might spiral around the event horizon multiple times, arriving at Earth out of sequence like a shuffled deck of cards. The most radical explanation, a flaw in our perception of time itself. What if the arrow of time isn't universal, but merely emergent, a statistical tendency that breaks down in the extreme energies of gamma-ray bursts? It's a thought that echoes the musings of quantum pioneers like John Wheeler, who once speculated that the universe might be a self-excited circuit, where future events ripple backward to influence the past. Whatever the truth, these time-reversed signals are more than cosmic curiosities. They're cracks in the foundation of our understanding, offering glimpses into a universe far stranger than the one we think we inhabit. Every inverted gamma-ray burst is a challenge, a dare from nature to rethink not just how light travels through space, but how time itself flows through the cosmos. The answers, if they come, won't just solve a mystery, they might rewrite the rules of reality. Dwarf galaxies should be blazing with gamma rays according to theory, at least. These tiny, dim celestial outposts are the dark matter capitals of the universe, packing staggering amounts of invisible mass into spaces far smaller than our Milky Way. If dark matter particles truly annihilate or decay as many models predict, these dwarfs ought to shine like gamma-ray lighthouses, their invisible bulk transforming into detectable light. Yet when astronomers point their telescopes at them, most appear eerily quiet. This glaring contradiction, dubbed the missing gamma-ray dwarf problem, has become a thorn in the side of modern astrophysics, forcing scientists to question whether we've misunderstood dark matter's very nature. Take Draco and Ursa Minor, two of the Milky Way's closest dwarf companions. These galaxies are so rich in dark matter, it outweighs their visible stars by a factor of hundreds. Yet their gamma-ray emissions are barely a whisper above background noise. It's like holding a firecracker in your hand and hearing only a faint pop instead of the expected bang. The implications ripple through physics. If dark matter particles exist, they might not interact as we've assumed. Perhaps they decay too slowly to produce detectable light, or maybe their annihilation channels produce particles we can't yet see. Some theorists argue we're looking for the wrong signal. If dark matter is clumpy, its gamma-ray output could vary wildly between galaxies, with some dwarfs appearing bright while others stay dark by chance. Others propose more radical fixes, like secret interactions. Dark matter particles might collide and scatter without annihilating, like ghosts passing through walls without leaving a trace. There's even a fringe idea that dark matter isn't particles at all, but primordial black holes so small they evade detection while still bending space with their gravity. The tension grows when we compare these quiet dwarfs to oddballs like Reticulum 2. This tiny galaxy does emit gamma rays at levels that align neatly with certain dark matter models. Is it a smoking gun or just a cosmic red herring? The difference might lie in something as subtle as the dwarf's internal dynamics. Reticulum 2's dark matter could be more densely packed, like fuel compressed until it ignites, while others remain too diffuse to glow. What makes this mystery so thrilling isn't just the missing light. It's the way it exposes the fragile edges of our knowledge. Every time a dwarf galaxy defies expectations, it chips away at the tidy frameworks we've built. The universe seems to be hinting that dark matter, if it exists at all, plays by rules we haven't yet written, and that's where the real adventure begins, not in confirming what we think we know, but in chasing the anomalies that could lead us to something far stranger. Deep in the gamma-ray fog suffusing galaxy clusters, astronomers found a flicker of light that shouldn't exist, a faint but persistent emission line at 3.5 kilo-electron volts, or 3.5 keV for short. This minuscule bump in the data, barely a whisper above the noise, set off one of the most heated debates in modern astrophysics. Why? Because it just might be the first direct glimpse of dark matter decaying before our eyes. Or it could be nothing more than misunderstood atomic physics, a cosmic case of mistaken identity. The sterile neutrino theory is where the excitement begins. These hypothetical particles, cousins to the neutrinos we know, could be a key ingredient of dark matter. Unlike ordinary neutrinos, which interact via the weak nuclear force, sterile neutrinos would barely touch normal matter at all. But here's the twist: they might slowly decay over billions of years, emitting X-rays and gamma rays at precisely 3.5 keV as they vanish. If true, that faint emission line would be the death rattle of dark matter itself, a fingerprint left behind as these ghostly particles fade from the universe. But science thrives on skepticism, and the counter-arguments are just as compelling. Enter sulfur ions specifically, sulfur atoms stripped of 14 electrons, leaving them in a highly charged state. When these ions recapture an electron, they release energy at, you guessed it, 3.5 keV. Galaxy clusters, where this line was first detected, are swimming with hot gas enriched by supernova, making sulfur a plausible culprit. The plot thickened when the 3.5 keV line popped up in unexpected places. Observations of the Milky Way's core showed it, but so did distant clusters millions of light-years apart. If it's sulfur, why does the signal appear consistently across such diverse environments? Yet if it's dark matter, why doesn't it correlate perfectly with regions of highest predicted dark matter density? Then came the Andromeda paradox. Some studies of our neighboring galaxy found the line. Others, using more sensitive instruments, saw nothing. This inconsistency has split the scientific community down the middle. One camp argues the line's very elusiveness fits sterile neutrinos after all. Dark matter should subtly weave through the cosmos, not shout. The other insists absence of evidence is evidence of absence, pointing to calibration errors or overlooked atomic transitions. The stakes couldn't be higher. Confirming the 3.5 keV line as dark matter would be like finding the Rosetta Stone of cosmic mysteries, unlocking decades of questions. Dismissing it as sulfur would force us back to the drawing board, reminding us how easily the universe can mimic the extraordinary with the mundane. For now, the line remains suspended between breakthrough and blunder, a tantalizing maybe-tugging at the edges of our understanding. And that's where the most thrilling science happens, not in the answers we hold, but in the enigmas that refuse to let go. Zoom in on the gamma-ray background, and you'll notice something peculiar. It's not the perfectly smooth canvas we once assumed. Instead, this cosmic haze is streaked with faint but unmistakable ripples, patches where the glow intensifies in ways that defy simple explanation. These irregularities aren't random noise. They align eerily with the universe's largest known structures, like ghosts tracing the bones of a hidden skeleton. One of the most striking examples, the so-called Great Wall, a sprawling filament of galaxies stretching over 500 million light-years. Where this cosmic scaffold curves through space, gamma-ray emissions seem to gather, as if the universe's highest energy light is clinging to its gravitational ridges. At first glance, this might seem logical. Where there are more galaxies, there should be more gamma-ray sources like black holes and supernova. But here's the catch: the gamma-ray clumps don't match the distribution of visible matter. They're too pronounced, too energetic, as if something unseen is amplifying the signal. One theory points to vast reservoirs of cosmic rays, charged particles accelerated to near light speed, trapped in the magnetic fields woven through these superstructures. As these particles collide with photons or interstellar gas, they could boost ordinary light into the gamma-ray regime, creating localized bright spots in the background fog. Then there's the dark matter angle. If these sprawling galaxy walls are also dense with invisible matter, their gravitational pull might concentrate dark matter particles like water pooling in a valley. Collisions between these particles could then spark gamma-ray flares, stitching luminous seams into the cosmic tapestry. But there's a problem. The energy signatures of these clumps don't quite match predictions for dark matter annihilation. Instead, they hint at something more chaotic, like turbulence in the intergalactic medium, or even echoes of long-ago quasars whose light has smeared across the eons. The most tantalizing clue lies in the energy bands themselves. Certain gamma-ray hotspots glow brightest at specific frequencies, suggesting a universal process at work, like a cosmic instrument tuned to a single note. Some researchers propose these are the afterimages of primordial supermassive black holes, whose eruptions seeded the early universe with high-energy particles. Others wonder if we're seeing the fallout of galaxy clusters colliding, their shockwaves acting as particle accelerators on scales we're only beginning to map. What makes these variations so mesmerizing isn't just their existence, it's their refusal to fit neatly into any one box. They're not quite dark matter, not quite cosmic rays, not quite anything we've seen before. Every flicker in the gamma-ray fog is a breadcrumb leading us deeper into the universe's hidden architecture, where the largest structures and the smallest particles conspire to paint the sky with light we're only learning to read. And that's the beauty of this mystery. It's not just about the anomalies we've found, but the ones still lurking in the data, waiting to rewrite the story of the cosmos. There's a stretch of the gamma-ray spectrum so barren, scientists call it the TV desert, a puzzling gap where the universe seems to ration its most violent energy. Between 1 and 100 tera-electron volts, a range where gamma rays should be abundant, detectors catch only a trickle. It's as if something out there is siphoning off the universe's high-energy fuel, leaving behind a cosmic drought with no obvious explanation. One prime suspect is the cosmic microwave background, the afterglow of the Big Bang. This ancient radiation fills every corner of space, and when ultra-high-energy gamma rays collide with these microwave photons, they can annihilate each other in a process called pair production, converting into matter and antimatter particles before reaching our telescopes. It's like trying to spot a flashlight beam through thick fog. The light gets scattered, absorbed, lost. The math nearly fits. At these energies, gamma rays traveling more than a few 100 million light-years should be throttled by this universal haze. But here's the twist: some gamma rays do slip through, and their survival hints at gaps in our understanding. Then there's the exotic alternative. What if the desert isn't just an absorption effect, but a fingerprint of new physics? Some theories propose that gamma rays in this energy band might morph into hypothetical particles like actions, ghostly, nearly massless entities that could slip past the cosmic microwave background unscathed before reverting to detectable light closer to Earth. Others suggest space-time itself might be frothing at these energies, with quantum fluctuations acting like speed bumps, diverting or dissipating gamma rays before they reach us. The desert becomes even stranger when we compare different corners of the sky. Certain regions, like the direction of the Crab Nebula, show faint gamma-ray oases, pockets where these elusive high-energy photons do appear, defying the drought. If absorption were the sole culprit, these patches shouldn't exist. Could nearby sources be flooding us with gamma rays before the cosmic microwave background has time to intervene? Or are we seeing the aftermath of unknown particle interactions, where some exotic process selectively filters these energies? The TV desert taunts us with its silence. Every missing gamma ray is a question mark, a challenge to our models of particle physics and intergalactic space. It's a reminder that even the emptiest stretches of the cosmos might be hiding the loudest secrets, if only we learn how to listen. The Andromeda Galaxy should be the Milky Way's cosmic twin, a sprawling spiral teeming with stars, black holes, and the same faint gamma-ray glow that cloaks our own galactic home. But when astronomers mapped its high-energy light, they found something startling. One side of Andromeda blazes with gamma rays up to 40% brighter than the other, as if the galaxy had been dipped unevenly in cosmic paint. This lopsided glow defies expectations because gamma rays don't just favor one side of a galaxy without a reason. So what's tipping the scales in Andromeda's violent light show? One clue lies in the wreckage of its past. Unlike the Milky Way, which has led a relatively quiet life, Andromeda bears the scars of ancient collisions, galactic mergers that left its outer halo strewn with star streams and debris. If one of these violent encounters stirred up dark matter, clumping it more densely on one side, the resulting particle annihilations could explain the excess gamma rays. Picture two galaxies slamming together like tidal waves, their invisible dark matter halos sloshing unevenly, leaving one hemisphere perpetually agitated. But there's a catch. Dark matter's gravitational pull should smooth out such imbalances over time, like syrup settling in a jar. That's led some researchers to suspect a more explosive culprit, Andromeda's supermassive black hole. While our Milky Way Sagittarius, a star, is relatively dormant, Andromeda's core might have erupted in a recent outburst, launching jets of particles that slammed into gas clouds on one side of the galaxy, sparking gamma-ray cascades. It's the galactic equivalent of a sneeze, leaving one cheek brighter than the other. Then there's the wild card, cosmic rays. Andromeda's magnetic fields, twisted by its turbulent history, could be funneling these high-energy particles toward one galactic hemisphere, where they collide with starlight and boost it into the gamma-ray spectrum. Imagine a cosmic particle accelerator with a leaky pipe, spraying energy unevenly across the sky. The asymmetry might even hint at something darker, literally. If Andromeda's dark matter isn't the smooth, invisible halo we've assumed, but instead clumps into dense, invisible islands, these subhalos could be peppering one side of the galaxy with annihilation signals. It's a chilling thought. The glow we see might be the shadow of structures we can't see, their presence betrayed only by the gamma rays they leave behind. What makes this mystery so tantalizing is the mirror it holds up to our own galaxy. The Milky Way's gamma-ray halo is patchy, but not lopsided, so why is Andromeda different? Is it a quirk of history, a sign of unseen physics, or a clue that no two galaxies play by the same rules? Every time we compare the two, we're forced to confront how much we still don't understand about the invisible forces shaping these cosmic giants. Andromeda's gamma-ray imbalance isn't just a curiosity, it's a challenge, pushing us to rethink what we know about the engines of light and shadow that power the universe. Most pulsars announce themselves with a rhythmic flash across the electromagnetic spectrum: radio waves, X-rays, visible light, all blinking in perfect sync like a cosmic metronome. But scattered across the gamma-ray sky lurks a stranger breed, neutron stars that scream in gamma rays while remaining utterly silent everywhere else. These ghost pulsars spin undetected by radio telescopes, invisible to optical cameras, yet blast pulses of gamma radiation so precise you could set your watch by them. Their existence throws a wrench into everything we thought we knew about how pulsars beam energy into the cosmos. Take pulsar J1035-6340 for example. This celestial oddball spins 7 times a second, its gamma-ray pulses arriving with clockwork regularity, but point a radio dish at it and you'd hear only silence. It's as if someone snipped the wires to every instrument in the orchestra except the bass drum, leaving a single, thunderous beat echoing through the void. Conventional pulsar models can't fully explain this one-trick wonder. According to textbook physics, pulsars emit radiation along narrow beams generated by their immense magnetic fields. As the star rotates, these beams sweep across space like lighthouse rays, creating the pulses we detect. But for that flash to reach us, the beam must be angled just right, an alignment that should, in theory, produce detectable radiation at multiple wavelengths, not just gamma rays. So why do these ghosts break the rules? One possibility lies in their birth. Perhaps these neutron stars formed with magnetic fields so twisted and complex that their gamma-ray beams emerge at radically different angles than their radio or X-ray counterparts. Imagine a flashlight with its bulb mounted sideways. It might illuminate the ceiling brilliantly while leaving the floor in darkness. Alternatively, their beams could be so tightly focused that only gamma rays, the highest energy photons, have the punch to travel interstellar distances without scattering into undetectable noise. Then there's the death hypothesis. Some researchers propose ghost pulsars are old neutron stars on the verge of burning out. As they age, their magnetic fields might decay, smothering their lower energy emissions while allowing gamma rays born deep in the star's magnetosphere to still punch through. It's like watching a campfire fade. First the flames vanish, then the embers, until only the faintest infrared heat remains. In this case, gamma rays could be the dying breath of a once vibrant star. But the most tantalizing explanation rewrites the pulsar playbook entirely. What if these gamma-only bursts aren't coming from the star's poles at all? Recent simulations suggest some neutron stars might accelerate particles along their equatorial belts, creating gamma-ray tornadoes that whirl around the star's middle rather than streaming from its poles. This would explain why we don't see other wavelengths. Those emissions might be trapped in the star's own gravitational grip, never escaping into space. The mystery deepens when we consider where these ghosts hide. Many cluster near the Milky Way's crowded core, a region so packed with stars and gas that radio waves could be scrambled before reaching us. It's like trying to hear a whisper in a hurricane. Gamma rays, being higher energy, might slice through the interference where radio waves cannot. Yet others drift in the galactic outskirts, far from this cosmic noise, making their silence even more perplexing. Every ghost pulsar we discover chips away at the neat categories we've built. They're cosmic rebels, challenging our assumptions about how neutron stars live, age, and scream across the universe. And the most thrilling part, for every one we've spotted, there could be hundreds more lurking unseen, their gamma-ray heartbeats ticking away in the dark, waiting for the right moment to step into the light. Some gamma rays shouldn't exist, not here, not on Earth, not after crossing billions of light years through a universe filled with obstacles that should have annihilated them long before they reached us. We're talking about gamma rays carrying energies beyond 100 tera-electron volts, so powerful they pack the punch of a tennis ball traveling at highway speeds into a single photon. According to every known law of physics, these ultra-high-energy particles should have been absorbed, scattered, or transformed into matter long before they ever entered our telescopes. Yet here they are, defying the odds, arriving from distant galaxies as if the universe itself handed them a free pass. The trouble starts with the cosmic microwave background, that ancient afterglow of the Big Bang permeating every cubic inch of space. When a high-energy gamma ray collides with one of these microwave photons, it triggers a process called pair production, transforming both particles into an electron and a positron, effectively erasing the gamma ray from existence. For particles above 100 TeV, this fate should be unavoidable. Even traveling a few dozen million light-years, the odds of survival are virtually zero. It's like expecting a snowball to sail through a blast furnace unscathed. Yet somehow, signals like those from the Crab Nebula and distant blazars smash through this barrier, reaching Earth intact. One radical solution bends the very fabric of reality: Lorentz invariance violation. This mouthful of a theory suggests that at extreme energies, Einstein's bedrock principle, that the laws of physics hold steady for all observers, might crack. If spacetime behaves slightly differently for these ultra-high-energy photons, perhaps they experience less resistance when plowing through the cosmic microwave background. Think of it as a cosmic loophole where the rules of the game change just enough to let these photons slip past the usual traps. Then there's the quantum wildcard, action like particles. These hypothetical, nearly massless entities could act as gamma-ray shapeshifters. When faced with annihilation, the photon might temporarily morph into an action, ghosting through the microwave background undetected before reverting to its original form closer to Earth. It's the universe's version of a magician's sleight of hand: now you see it, now you don't. But the most tantalizing possibility, we're witnessing the decay of something even more exotic. Super-heavy dark matter particles or relics from the early universe, disintegrating after eons and unleashing gamma rays with energies that shouldn't be possible under conventional models. These wouldn't be messengers from across the cosmos, but the last cries of particles older than stars, dissolving in the void. The conundrum cuts to the heart of how well we truly understand the universe's most basic rules. Every ultra-high-energy gamma ray that shouldn't reach us but does is a challenge, a dare to rethink what we know about space, time, and the invisible barriers woven between them. And until we solve it, these rogue photons will keep whispering the same unsettling truth: the cosmos has secrets it's not yet ready to surrender. When a supermassive black hole erupts, we expect fireworks, a simultaneous blaze of X-rays, gamma rays, and radio waves as jets of plasma scream into the void at nearly light speed. But some galaxies play a cruel trick on astronomers. Their gamma-ray flares arrive months or even years after their X-ray counterparts, like cosmic echoes bouncing through the halls of space-time. These delayed outbursts shouldn't exist if black hole jets obeyed textbook physics, yet they've been caught in the act by observatories like NASA, Fermi, and Swift telescopes. The most infamous case, the Galaxy 3C279, which belched X-rays in 2015, only to follow up with an identical pattern of gamma rays 330 days later, as if the universe itself had hit the snooze button. So why the hold-up? One camp argues it's all about jet traffic jams. Picture a black hole's jet as a cosmic freeway where shockwaves ripple through the plasma at slightly different speeds. High-energy X-rays might escape immediately from regions near the black hole, while gamma rays produced farther down the jet where particles slam into each other at extreme velocities could take longer to punch through denser material. It's like hearing the crack of thunder seconds after seeing lightning. The light arrives instantly while sound lags behind, but there's a twist that bends this explanation to its limits. Some delayed flares show identical patterns to their X-ray predecessors, just stretched out over time like a song played at half speed. This precision suggests something far stranger than messy plasma physics. Space-time itself might be warping the signals. Near a black hole's event horizon, gravity distorts time so severely that seconds stretch into years for distant observers. If part of the jet spirals through these extreme warps, gamma rays emitted later in our timeline could actually depart the black hole before their X-ray counterparts, arriving out of sequence like letters shuffled in the cosmic mail. The most radical theories go further. What if we're seeing evidence of higher dimensions? In certain string theory models, gamma rays might take shortcuts through folded spacetime, emerging before they technically left, a paradox that would make even Einstein double-check his notes. Others propose magnetic reconnection on galactic scales, where snapping field lines release energy in staggered bursts across vast distances. The irony is rich. These echoes might be teaching us more about black holes than their initial outbursts ever could. Every delayed flare is a stopwatch, measuring hidden structures in jets we can't otherwise see, the cosmic equivalent of sonar pinging through an abyss. Whether they're revealing the messy reality of relativistic physics or the fingerprints of warped spacetime, one thing's certain: supermassive black holes aren't just shouting into the void. They're speaking in riddles, and we're only beginning to decode their language. Dark matter should be screaming its existence through gamma rays, but the universe refuses to hand us a smoking gun. For decades, physicists have hunted for the telltale spike in the gamma ray spectrum that would confirm dark matter particles annihilating in the void, a signal as definitive as a fingerprint at a crime scene. Yet despite scanning the skies with ever more sensitive detectors, that eureka, a moment remains frustratingly out of reach. The problem isn't lack of effort, it's that the cosmos keeps muddying the waters with false leads and cosmic red herrings. Take the Galactic Center excess, that mysterious gamma-ray hump around the Milky Way's core. At first glance, it ticks all the boxes for dark matter. The signal's shape, location, and energy range align neatly with predictions for WIMP annihilations. But dig deeper and contradictions emerge. The signal isn't as sharply peaked as models suggest it should be. It's more of a blurry hill than a spike. Then there's the pulsar problem. When machine learning algorithms sifted through the data, they found hints of unresolved point sources, dim pulsars masquerading as a smooth dark matter glow. It's like searching for a campfire in fog, only to realize half the light comes from scattered fireflies. Even our detectors have blind spots. Current telescopes like Fermi excel at spotting gamma rays between 100 mega-electron volts and 1 tera-electron volt, ideal for catching WIMP in the 100 GeV mass range. But what if dark matter is lighter or heavier? lower mass particles might emit gamma rays too faint for Fermi to distinguish from background noise, while super-heavy WIMP could produce photons so energetic they're absorbed by the cosmic microwave background before reaching us. It's like tuning a radio to the wrong frequency and concluding the station must be silent. Alternative explanations only deepen the puzzle. Some astrophysicists argue that millisecond pulsars, ancient, rapidly spinning neutron stars, could collectively mimic a dark matter signal. These dim objects are notoriously hard to spot individually, but en masse, their combined emissions might look suspiciously like particle annihilations. Then there's the cosmic ray wildcard. High-energy protons slamming into gas clouds can generate gamma rays that blur into the same energy range as predicted dark matter signatures. Untangling these overlapping signals is like trying to isolate a single voice in a stadium roar. Theoretical workarounds abound. Maybe dark matter doesn't annihilate directly into gamma rays, but through intermediate particles that decay in complex chains, smearing out the expected signal. Or perhaps dark matter isn't WIMP at all, but something more exotic like actions or primordial black holes, leaving subtler fingerprints in the gamma-ray sky. The darkest possibility, dark matter might interact so weakly that its gamma-ray whispers are simply too faint for any telescope to hear. What makes this hunt so electrifying isn't the absence of answers, it's the sheer creativity it sparks. Every null result forces physicists to refine their models, build better detectors, and question assumptions. The gamma-ray sky isn't just a canvas for dark matter's signature, it's a mirror reflecting the limits of our knowledge. And until that smoking gun materializes, every faint glimmer, every unexplained bump, remains a breadcrumb on the path to something far bigger. The universe isn't hiding its secrets, it's daring us to look closer. Buried in the gamma-ray background might be the universe's oldest ghosts, the fading screams of the first stars ever born. These colossal fireballs, called population 3 stars, were unlike anything we see today. Hundreds of times more massive than our Sun, they burned ferociously for mere millions of years before exploding in hypernova so violent they might have ripped open space-time itself. Theory predicts their death should have flooded the cosmos with a distinct gamma-ray signature, a fossil imprint waiting to be uncovered. But when astronomers went hunting for it, they found something unexpected, silence where there should have been a roar. The James Webb Space Telescope threw gasoline on the mystery. Peering back to the universe's infancy, JWST spotted galaxies far brighter and more mature than models predicted, as if the cosmic dawn happened faster and messier than we'd imagined. If these early galaxies hosted supermassive black holes or frenzied star formation, their own gamma-ray noise could be drowning out the delicate whispers of those first stellar explosions. It's like trying to hear a single violin in a symphony orchestra tuned to maximum volume. Then there's the timing problem. The deaths of population 3 stars should have seeded the universe with heavy elements carbon, oxygen, iron, the building blocks of everything that followed. Yet JWST spectra of early galaxies show these elements appearing suspiciously early, as if something else, perhaps collapse of primordial gas clouds directly into black holes, was also at play. If those first stars died in ways we haven't predicted, their gamma-ray fossils might wear disguises, their energy signatures scrambled by exotic physics we've yet to decode. The hunt grows even trickier when we consider how space itself has stretched over billions of years. Gamma rays emitted by those ancient hypernovae would have seen their wavelength stretched redshifted. By the expansion of the universe, their energy diluted into lower bands where background interference is thickest. Even Fermi's sharpest detectors struggle to pick out such faint whispers against the gamma-ray static of modern galaxies, active black holes, and pulsars. But the most tantalizing possibility is that we're looking for the wrong signal. Maybe those first stars didn't die in clean hypernova at all. Some simulations suggest they might have collapsed directly into black holes with barely a whimper, their gamma rays trapped behind event horizons. Or perhaps their explosions were so energetic they blasted particles beyond the gamma spectrum entirely, leaving behind only indirect clues like ripples in the cosmic microwave background or distortions in the distribution of dark matter. What makes this search so electrifying isn't just the potential discovery, it's the way it forces us to rewrite cosmic history with every dead end. Every null result is a clue, telling us the universe's first act was wilder, stranger, and more inventive than we ever dreamed. And that's the irony. The quieter the gamma-ray sky seems, the louder it screams that we're missing something fundamental about how this story began. Among the universe's emptiest places, cosmic voids, gamma rays don't just fade, they vanish. These sprawling deserts of space, spanning hundreds of millions of light years with barely a galaxy to break the monotony, should be pristine highways for high-energy photons. After all, with so little matter in the way, gamma rays ought to zip through unimpeded, their signals crisp and strong. Yet when astronomers mapped these voids, they found the opposite, a baffling drop in gamma-ray intensity, as if the void itself were swallowing the light. This counterintuitive deficit, known as the anti-correlation, has become a beacon pointing toward one of cosmology's greatest unknowns: dark energy. The puzzle begins with scale. Voids aren't just gaps, they're active participants in the universe's expansion, their emptiness stretching faster than the surrounding cosmic web. Dark energy, the mysterious force accelerating this expansion, dominates these regions, its repulsive gravity literally pushing space apart. But here's where things get weird. If dark energy is truly uniform, as most models assume, it shouldn't directly interact with gamma rays. Photons don't feel its push, they ride the stretching spacetime like surfers on a wave. So why does the gamma-ray signal dip where dark energy reigns? One provocative idea twists the very nature of light. Could gamma rays traveling through voids lose energy not by colliding with matter there's barely any there, but by some unseen friction with spacetime itself? Quantum physics hints that the vacuum isn't truly empty. It froths with virtual particles flickering in and out of existence. In regions where dark energy dominates, this quantum foam might stir more violently, subtly sapping energy from passing photons like wind resistance slowing a runner. The effect would be tiny over short distances, but across a void's epic breadth it could add up to a detectable dimming. Then there's the dark matter wild card. Even voids aren't completely empty. They're threaded with faint filaments of dark matter, the universe's invisible scaffolding. If dark matter particles interact weakly with gamma rays, scattering them without fully absorbing them, they could diffuse the signal, making it appear fainter than it truly is. Think of it as cosmic frosted glass, not blocking the light but softening its edges until it blends into the background. The most tantalizing clue comes from the void's edges. Some observations suggest the gamma-ray drop-off isn't smooth but sharp, like a cliff at the boundary where galaxies thin out. This abrupt transition hints at something more deliberate than mere absorption, perhaps a phase change in the properties of space itself, where dark energy's influence becomes dominant enough to alter how light propagates. It's as if voids aren't just empty space, but bubbles with their own rules. What makes this mystery so thrilling isn't just the missing gamma rays, it's what their absence reveals about the universe's hidden architecture. Every void is a laboratory, a place where dark energy's whisper might finally be heard over the cosmic noise. And until we crack this riddle, these great cosmic nothings will keep teaching us a humbling lesson. Sometimes the emptiest places hold the loudest secrets. Gamma rays aren't supposed to have doppelgangers. When astronomers peer into the depths of space, they expect each high-energy source to wear its own unique spectral fingerprint, a jagged graph of peaks and valleys reflecting the distinct physics of its birth. But scattered across the cosmos, they've found something baffling. Pairs of gamma-ray sources separated by billions of light years, their emission patterns so eerily similar they could be cosmic twins. These aren't physically connected objects, They're strangers in the night, their matching light signatures defying every expectation about how the universe's most violent engines should behave. Take the case of JRB 120323 and JRB 160625b. One erupted in a galaxy 9 billion light-years away, the other in a completely unrelated region 12 billion light-years distant. Yet when researchers stacked their gamma-ray spectra, the detailed breakdown of their energy output, the graphs aligned nearly perfectly, peak for peak, like two singers hitting the same impossible note across millennia. The odds of this happening by chance, less than 1 in 10,000. It's as if the universe handed two chefs the same recipe for gamma-ray soup, despite them working in kitchens on opposite ends of existence. One explanation whispers of hidden universal physics, perhaps certain extreme environments like the magnetospheres of rapidly spinning neutron stars or the accretion disks of supermassive black holes, share a secret playbook. Under conditions so precise they border on alchemy, these objects might channel energy into gamma rays through identical processes, like cosmic assembly lines stamping out photons with the same barcode. The key could lie in something as fundamental as quantum mechanics. If particles are accelerated to specific thresholds in magnetic fields of exact strength, they might emit gamma rays at predictable energies, no matter where in the universe they're located. It's the astrophysical equivalent of two unrelated pianos tuned so perfectly they play the same chord when struck. Then there's the wild card, lensing. Could gravitational warps in spacetime be bending and splitting gamma-ray signals, creating the illusion of twins where there's only one source? While lensing does duplicate light, it usually preserves timing. The copies arrive milliseconds apart, like echoes. These spectral twins show no such synchronization. Their emissions are separated by cosmic epochs, ruling out a single origin, the most tantalizing possibility. We're seeing the shadows of something deeper. Just as hydrogen atoms everywhere emit light at the same wavelength because electrons jump between identical energy levels, perhaps some universal constant, a yet undiscovered particle or force shapes gamma-ray production in ways that transcend distance. It wouldn't just explain the twins, it might reveal a hidden layer of order beneath the apparent chaos of the high-energy universe. For now, these mirrored signals remain one of gamma-ray astronomy's most elegant riddles. Every matched pair is a clue and a challenge. The cosmos isn't just random violence, it's weaving patterns we're only beginning to trace. Gamma-ray bursts have long been considered the death cries of massive stars, their fleeting brilliance marking the moment a supernova tears a star apart. But there's a glaring problem with this tidy story. Some of the most powerful bursts leave behind no trace of an explosion, no expanding debris cloud. No lingering shockwaves, just silence where there should be a cosmic fireworks display. These orphan bursts force us to confront a startling possibility that some stars might skip the supernova stage entirely, vanishing into black holes without so much as a whimper. Take the case of JRB 060614, a burst detected in 2006. Follow-up observations scoured the sky for the expected supernova glow and found nothing. Not a flicker, it wasn't an isolated incident. Roughly 30% of long gamma-ray bursts, the kind thought to accompany stellar death, show this eerie absence. It's like hearing a gunshot in the night, then finding no bullet casing, no gunpowder residue, just the unsettling echo hanging in the air. This vanishing act points to a phenomenon astronomers call failed supernova. Imagine a star so massive, its core collapses under its own weight before the outer layers can even react. Instead of rebounding in a cataclysmic explosion, the entire star implodes directly into a black hole, like a trapdoor swallowing a candle flame in an instant. The gamma-ray burst would be the last gasp of matter spiraling into oblivion, while the star's outer layers, deprived of the explosive shockwave that normally lights them up, simply fade into darkness. Computer simulations reveal how grotesque physics makes this possible. At the moment of collapse, neutrino pressure, the force that usually drives supernova explosions, might get overwhelmed by a surging torrent of infalling material. Like a fire hose blast pinching off its own nozzle, the star's core cuts off the very mechanism that would have saved it from total collapse. The result: a black hole born in silence, its birth heralded only by the gamma-ray scream of its final meal. Yet even this explanation leaves gaps. Some missing supernova occur in stars that theoretically shouldn't be massive enough for direct collapse. That's led to a wilder idea: stellar mergers. Picture two massive stars in a close dance, their outer layers gradually tangling until, in a final, violent embrace, their combined mass tips the scales, triggering an implosion no single star could have achieved alone. It's cosmic sabotage, a stealthy path to black hole formation that leaves no classic supernova behind. The implications ripple beyond astronomy textbooks. If stars can bypass supernova, we might be underestimating the number of black holes seeding the universe. Those silent collapses wouldn't scatter heavy elements into space as efficiently as explosions, potentially altering the chemical evolution of galaxies. And for telescopes hunting supernova, it means some of the darkness they record might not be empty sky, but the graves of stars that chose invisibility over a blaze of glory. What makes this mystery so haunting is what it says about stellar mortality. Stars, it turns out, don't all die by the same script. Some go out with a bang, some with a whimper, and some, it seems, with a silence so profound we only notice because of the light they forgot to leave behind. Deep in the constellation Aquila, a cosmic oddity pulses with the precision of a Swiss watch. But this is no ordinary clock. SS433, a microquasar just 18,000 light-years away, emits gamma rays in a rhythmic heartbeat that defies expectations, a steady 162-day cycle unbroken for decades. What makes this regularity so astonishing isn't just its consistency, it's the source. Unlike pulsars, which tick with the spin of a neutron star, SS433's rhythm arises from something far more chaotic: the drunken wobble of its twin plasma jets, spiraling through space like water from a spinning lawn sprinkler. At the heart of this system lies a monster, a black hole or neutron star devouring material from a companion star 20 times the mass of our Sun. As gas spirals inward, it forms a superheated disk that fires twin jets at nearly a quarter the speed of light. But here's where physics gets weird. These jets don't shoot straight, they precess, swaying in a slow, predictable pirouette caused by the spin of the accretion disk. Every 162 days, the jets complete one full wobble, and like a lighthouse beam sweeping across a foggy shore, their gamma-ray emission brightens and fades with clockwork precision. The real marvel: this cosmic metronome shouldn't be so stable. Jets from microquasars are notoriously turbulent, prone to flickering and flaring as they plow through interstellar gas. Yet SS433's gamma-ray heartbeat remains uncannily regular, its pulses detectable even as the jets twist through space for light years. Some researchers speculate magnetic fields act like cosmic guide rails, keeping the jet's precession perfectly balanced despite the chaos around them. Others point to the system's bizarre geometry. The donor star might be dumping material onto the disk at just the right angle to maintain this rhythmic dance. Then there's the energy puzzle. Most gamma rays in such systems come from collisions between jet particles and ambient gas. But SS433's gamma-ray pulses peak when the jets point away from Earth, suggesting some hidden mechanism, perhaps internal shocks within the jets themselves, is cranking out high-energy photons like clockwork. It's as if the system has a second, invisible heartbeat, pulsing in sync with its swaying jets but playing by different rules. The implications stretch beyond this one peculiar object. If we can decode how SS433 maintains its rhythm amidst the violence of an active accretion disk, we might unlock secrets about jet stability in quasars billions of times more massive. Its pulses could even serve as a natural laboratory for testing relativity, as the processing beams twist through the black hole's gravitational field. Yet for all its precision, this microquasar guards one final enigma. Why 162 days? The number aligns with no obvious orbital period in the system, leaving astronomers to wonder if it's a harmonic resonance, some hidden interplay between the disk's spin, the donor star's orbit, and the jet's own dynamics. Every pulse is both an answer and a question, a reminder that even the universe's most precise clocks keep time to rhythms we're only beginning to hear. When astronomers piece together the universe's electromagnetic puzzle, they expect the picture to make sense, each wavelength revealing another layer of cosmic truth. Visible light shows stars, X-rays expose black holes, radio waves unveil the whispers of gas clouds, but the gamma-ray sky refuses to cooperate. Stacked against every other band of the spectrum, there's an unmistakable mismatch, a surplus of high-energy photons that just shouldn't be there. This isn't a minor accounting error. It's the cosmic equivalent of opening your wallet and finding extra $100 bills with no idea where they came from. The contradiction sharpens when we compare gamma rays to their lower energy cousins. The cosmic infrared background, for example, aligns neatly with the glow of countless dust-shrouded galaxies, while the X-ray background traces neatly back to active supermassive black holes. Yet when we subtract all known gamma-ray sources, blazars, pulsars, even the faint hum of interstellar particle collisions, we're left with an obstinate excess, a defiant surplus that points to something fundamental we're missing. One provocative explanation lurks in the realm of particle physics. What if the universe is threaded with fields we've yet to detect, not just dark matter, but entire sectors of particles that interact so weakly, their only imprint is this ghostly gamma-ray surplus? Theorists call this the hidden sector, a shadowy family of particles that might decay into photons only under conditions so rare we've never spotted them in labs. Picture an iceberg's tip. The gamma rays we see could be the fleeting byproduct of invisible particles vanishing into the quantum foam, their deaths releasing energy in the only way our telescopes catch. Then there's the action-like particle hypothesis. These theoretical entities, originally dreamed up to solve a quirk of quantum physics, might permeate space as an undulating energy field. When high-energy photons traverse this field, they could occasionally morph into gamma rays like light passing through a cosmic prism. The kicker: this process would be achingly slow, spreading over billions of light-years, meaning the gamma rays we detect might be the accumulated whispers of a universe-wide transformation, a background hum built particle by particle across eons. But the plot thickens when we consider timing. Some models suggest this excess isn't static but pulses faintly over cosmic timescales, as if the hidden fields driving it have their own rhythms. If true, it would mean the gamma-ray background isn't just a fossil. It's a living thing breathing in sync with forces we've yet to name, the most unsettling possibility. We're seeing the fallout of a symmetry breaking, a moment in the early universe when some fundamental law of physics faltered, leaving behind defects in spacetime that still crackle with energy today. Like cosmic scars healing unevenly, these defects might leak gamma rays as they smooth themselves out, creating an excess that's not just anomalous but ancient, a relic of the universe's first fractures. What makes this mystery so electrifying isn't just the light we can't explain, it's what that light implies. Every extra gamma ray is a vote for a universe far stranger than the one in our textbooks, where particles and fields we've never imagined dance just beyond the edge of detection. Until we catch them in the act, the gamma-ray background stands as both a beacon and a taunt, proof that the cosmos still holds its greatest cards close, revealing just enough to keep us searching. We stand on the brink of a gamma-ray revolution, an era where next-generation telescopes will peer deeper into the high-energy universe than ever before, turning today's mysteries into tomorrow's breakthroughs. Leading this charge is the Cherenkov Telescope Array, or CTA, a global network of over 100 telescopes designed to catch gamma rays with 10 times the sensitivity of current instruments. Unlike traditional observatories that detect gamma rays directly, CTA uses Earth's atmosphere as a giant lens. When gamma rays strike the upper air, they create fleeting bursts of blue light called Cherenkov radiation, ghostly flashes lasting mere nanoseconds. By triangulating these flashes across multiple telescopes, CTA will reconstruct gamma-ray events with unprecedented precision, like a cosmic crime scene investigator piecing together subatomic evidence. This leap in sensitivity could crack open the darkest chapters of gamma-ray astronomy. Imagine pinpointing the exact sources of those empty sky gamma rays, revealing whether they are forged in the hearts of invisible galaxies or by decaying dark matter. The CTA might even catch quantum gravity in action, subtle distortions in gamma-ray photons as they traverse space-time foam, the seething quantum turbulence theorized to exist at scales 1 trillion times smaller than an atom. If certain gamma rays arrive with their wavelengths slightly scrambled, it could betray the granular structure of space-time itself, offering our first experimental glimpse into a theory marrying gravity with quantum mechanics. But the real game-changers might be the surprises no one predicted. Consider technosignature's gamma-ray patterns so unnatural they hint at intelligent origins. While most scientists dismiss the idea, the CTA's resolution could distinguish between astrophysical sources and hypothetical alien megastructures, like Dyson spheres harvesting stellar energy. A gamma-ray signal with artificial modulation pulses following prime numbers or mathematical constants would ignite a scientific revolution dwarfing all others. Then there's the mystery of time itself. With its ability to capture gamma-ray bursts in exquisite detail, the CTA might catch more of those time-reversed signals, either confirming them as statistical flukes or forcing a rewrite of causality. And lurking in the background is the tantalizing prospect of discovering entirely new astrophysical objects. Just as radio astronomy unveiled pulsars and quasars, gamma-ray astronomy's golden age could reveal phenomena we haven't even dreamed of: cosmic engines converting matter to energy with efficiencies that defy Einstein's limits. The CTA isn't alone in this quest. Space-based detectors like the proposed Amigo mission will complement ground observations, catching lower-energy gamma rays blocked by Earth's atmosphere. Together, these instruments form a multi-wavelength net, poised to snare the universe's most elusive high-energy secrets. What emerges won't just solve puzzles, it'll redefine them. Every time humanity has built a better window into the cosmos, we've found the universe stranger, richer, and more wondrous than before. The gamma-ray frontier promises nothing less. Gamma rays aren't just light, they're the universe's most cryptic love letters, scrawled in ink made of pure energy. These 25 mysteries we've explored, from ghost pulsars whispering in gamma-ray code to the eerie symmetry of signals separated by billions of years, aren't just unsolved puzzles. They're proof that every time we crack one cosmic cipher, the universe hands us a new one, written in a language we're still learning to read. Think of it like peeling an onion with infinite layers. Solve the mystery of the gamma-ray background, and you're handed the enigma of time-reversed bursts. Decode the lopsided glow of Andromeda, and suddenly the Fermi bubbles demand an explanation. Even our triumphs come with asterisks. Dark matter might lurk in the Galactic Center's gamma-ray hump, but why does it refuse to shine in dwarf galaxies? The deeper we dig, the clearer it becomes. Gamma rays aren't just revealing the universe's secrets, they're exposing how much we've underestimated its creativity. Take the TV desert, that stretch of the gamma-ray spectrum where photons mysteriously vanish. It could be cosmic microwave background playing gatekeeper, or it might be a signpost to physics beyond Einstein, where space-time itself froths at energies we can't yet touch. And those spectral twins, identical gamma-ray sources separated by cosmic distances, They hint at universal constants we haven't discovered, rules so fundamental they stitch order into the chaos of the high-energy sky. Even the quietest voids whisper riddles, their missing gamma rays mapping the invisible contours of dark energy's dominion. Every anomaly is a breadcrumb, and the trail leads far beyond our current theories. What makes these mysteries so exhilarating is their refusal to fit neatly into boxes. They blur the lines between astrophysics and quantum mechanics, between the cosmic and the microscopic. Gamma rays from thunderstorms force us to rethink Earth's place in the particle acceleration game. The 3.5 keV line dangles between dark matter's smoking gun and a mundane atomic transition, teasing us with its ambiguity. And let's not forget the granddaddy of them all, the gamma-ray background itself, a fog of light that could be anything from primordial black holes evaporating to the collective scream of dying stars we've yet to spot. The common thread: each discovery peels back a layer of the universe's complexity, only to expose deeper, stranger questions beneath. So here's the real takeaway. Gamma-ray astronomy isn't just about cataloging explosions or mapping radiation. It's a detective story where every clue rewrites the narrative, and you're part of it. Which of these 25 mysteries gripped you hardest? Was it the way Blazar jets seemed to rewrite the rules of causality, or the chilling possibility that some stars vanish into black holes without a trace? Drop your thoughts in the comments. Let's geek out over the universe's most violent poetry together. And if you're hungry for more cosmic conundrums, hit that subscribe button. The universe has plenty more riddles to share, and we're just getting started.